Welcome back, calculus students, to the fourth and final portion of the video notes for infinite limits and curve sketching. We're finally putting it all together, everything we've learned, and taking a calculus approach to sketching the graph of a function without the use of a calculator. So taking a look at the second example, we want to go through our process, starting with identifying the domain. So looking at this denominator, it looks like I'm going to have some excluded values when 1 minus x squared could equal 0. That's when 1 is equal to x squared, which means it can occur when x is equal to positive or negative 1. So the first step is to identify that the domain is all real numbers excluding negative 1. And I'm going to go ahead and write that in interval notation instead. So that's negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. Let's make sure we can fit that. Okay, there's my domain. Next, I want to identify the x and y intercepts. So the y-intercept is when you plug in 0, and that is going to give us 0 because of the numerator. And then this point also represents the x-intercepts. X-intercepts of a rational function come from the zeros of the numerator, or what values of x make the numerator equal to 0. So the x and y intercepts are both 0, 0. Next, we're going to evaluate the limits at infinity for this rational function. So let's start with the limit as x approaches positive infinity. And I'm going to go ahead and factor out that x squared from both the numerator and denominator, which will leave me with 1 over 1 over x squared minus 1. I don't like the way that looks. If I take the x squared out of each term. And so we know that the limit as x approaches infinity of 1 over x squared is 0. That's going to get closer and closer to 0 as x gets infinitely large, which leaves us with a limit of negative 1. So my horizontal asymptote is negative 1. On the right side, on the left side, as x approaches negative infinity, the 1 over x squared still approaches 0, so that's not going to change. And I am ready to lay down some initial graphing here. I've got a horizontal at negative 1, and I've got 0, 0 as a clear point on my function. Next, we are going to identify vertical asymptotes. And so the vertical asymptotes from the function are actually those domain restrictions that we identified earlier. We knew that x could not be equal to positive or negative 1. So we have vertical asymptotes at positive and negative 1. And that's going to look like this and this. Next step is to take the derivative of our function, and that we're going to do that using the quotient rule. So bust out your quotient rule from memory. We've got the derivative of the first function, which is 2x, times the denominator, minus the numerator times the derivative of the denominator, all over the denominator squared. Now we're looking for our critical values, so we're going to simplify this as much as possible, but we're not really going to care for the denominator here. The only thing the denominator tells us are the portions where the derivative does not exist, which we already knew because we already identified those as vertical asymptotes. So those are not going to be critical values, those are vertical asymptotes, and we can pretty much ignore our denominator. For solving this equal to 0, we're going to go ahead and distribute our numerator, which is 2x. Ooh, I bet you could factor that. I'm going to go ahead and try and factor it because factoring is such a great strategy. I guess I would still write the 2x. I'm going to factor the 2x out of the problem. That's going to leave me with 1 minus x squared from the first term. And then if you see this double negative here, we're going to say plus x squared for the second term. Those x squareds cancel, and so this whole thing is going to simplify to be 2x. And so it turns out that this 0, 0 point, this x and y intercept, is also a critical value. It's going to represent either a minimum or a maximum of the function. Based on the location of the horizontal asymptote, this is probably a minimum. So let's consider the derivative. I do want to go ahead and simplify this now that I know how much it does simplify. We've got just 2x over 1 minus x squared. Keep in mind, because the denominator has been squared, it is always positive. That's guaranteeing a positive value. So if I'm going to plug in a number less than 0 and a number more than 0, when I plug in a negative to this numerator, I'm going to get a negative. And when I plug a positive, I'm going to get a positive. That tells me that the function is decreasing leading up to this minimum and increasing after it. And now I'm confident that the middle portion of the function looks like an upward-facing parabola. Last step is to, that's really interesting. We need to consider what it's doing after 1 in our sign chart. So I kind of disregarded the 1 and the negative 1 as critical values. But we do actually need to consider those. So I'm just going to change this. In fact, this is this isn't good, because if you plugged in 1 and negative 1, you would get undefined. Woo-wee! Let's just back that up a little bit. That line did not work for me. 1 and negative 1 are critical values and need to be in our sign chart. They just can't qualify as minimums and maximums because they represent asymptotes. Whew. Okay. All critical values need to go on your sign chart. So negative 1 and 1 are critical values because they make the denominator 0, which means the derivative is undefined. 0 is a critical value because it represents where the derivative is equal to 0. There we go. Our test values now, that I have to be a little bit smarter about it, 0.5, positive, positive, negative 0.5, negative, negative. Now let's consider a number less than negative 1, like negative 2. If we plug in negative 2 to this function, we are going to get a negative in the numerator, and then 1 minus negative 2 squared is 1 minus 4, which is negative 3, but that's going to get squared, so that argument earlier is still valid, which means the function has to decrease on this left side of the asymptote. Like so. And then on the other side, if I plug in positive 2, I'm going to get a positive in the numerator, a positive in the denominator, and I know that my function has to increase on the other side of the asymptote. Keep in mind I can't draw it up above because then it would be decreasing in order to approach its asymptotes. Let's take a look at where the inflection point is. This is an interesting problem to identify inflection points because you can see the function is concave down, concave up, and then concave down again. So where exactly is it changing inflection? We're going to take a derivative again. So if you remember, our first derivative, fully simplified, was 2x over 1 minus x squared, and then we're going to use the quotient rule. So we've got our derivative of our numerator times our denominator minus our numerator times the derivative of our denominator utilizing the chain rule. Ooh, oh, I'm running out of room. Times an additional negative 2x. So I can say it out loud, but I can't quite get it in my window. All over the denominator squared, and since the denominator was already squared, this is going to make it to the 4th power. Simplifying this numerator, I'm going to use some red just to make it more distinctive. These negatives are going to cancel. And we've got 2x times 2 times 2x, which is 8x. Just make a note of that. So I'm going to factor out a 2 and a 1 minus x squared from each term. Oh, I'm still in red. 2, 1 minus x squared. That's going to leave me, if you take out the 2 in one of these terms, you've got a 1 minus x squared left over, plus, Let's take out one of these 2's. You're going to be left with 4x squared, and then this whole term in the parentheses has been removed. So go ahead and close parentheses there. All over your common denominator that has not changed, 1 minus x squared to the 4th. And going just a little bit further, that leaves us with 1 minus x squared over 1 plus 3x squared. All over 1 minus x squared to the 4th. So inflection points. We have critical values at 1 and -1 because those values will make the denominator equal to 0. And then the numerator is going to be equal to 0 also at 1 and -1. And then this one over here cannot be equal to 0 because you have a positive plus a positive. So -1 and 1 are the only potential critical values. We can test 0, 2, and -2. And we're going to be plugging them into the second derivative, and I would highly recommend using a calculator to test this. You have an inflection point when the sign of the second derivative changes from positive to negative or negative to positive. And remember that the sign of the second derivative is the concavity. So I'm going to be switching to my graphing calculator emulator to evaluate this function. All right, I have to do this off screen just a tiny bit so that I can still see my second derivative. I am going to type the equation of the second derivative into my calculator emulator. And that is 1 minus x squared, 1 plus 3 x squared. I could do this in my mind, and so could you, just evaluating your positives and negatives. But when the function gets a little more complex, I just prefer to trust my calculator to make sure I'm not making any strange mistakes. So let's look at a table of values. As you can see, -2 is negative, and 0 is positive, and +2 is negative. So completing my sign chart, over here I had negative, positive, negative, which actually means that these asymptotes are our inflection points. Inflection at -1 and +1. And so I've sketched this rational function with a calculus approach. This was supposed to be the last part of the video notes, but we actually still have 2 more examples, and it seems like each example is quite time-consuming, so I will see you back for a 5th video where we're going to attempt to finish both of the remaining problems.